Hello, my name is Dorothy Harris, and this is my ECE 591 final project presentation titled Spatiotemporal Transformer for Long Sequence Time Series Forecasting. This project focuses on spatiotemporal forecasting of long sequence time series. Current models for LSTF work well in temporal dimensions, but do not take spatial dimensions into account. It is important to work with both spatial and temporal dimensions because many real-world applications require it and can be improved upon from it. A high prediction capacity is needed in long sequence time series forecasting, as well as with dealing with spatiotemporal forecasting. To combat this, transformers can be used due to their ability to increase prediction capacity. This project was built off of a previous LSTF temporal transformer model and made spatiotemporal for better predictions on new related data. There are many uses for this model, such as in predicting solar power based on data of locations nearby, and electricity usage of households in a neighborhood. For my project, the model I chose to branch off of was the Informer Transformer model. This model was created in 2021 and received the AAAI Best Paper Award in that year. It is a transformer model specifically designed for long sequence time series forecasting, and its most stellar contribution was its use of a new self-attention specifically designed to combat issues transformers have with time complexity and memory usage. On the left is an example of some of the results of this model in comparison to other LSTF models, as well as the Informer model using regular self-attention instead of their new prob-sparse self-attention to prove how it enhanced the model. This project is an extension of the research I am currently doing. Because of this, every step in this project had to be done carefully and correctly. It was also figured out throughout this project more and more parts that had to be learned and implemented in order to accommodate adding a spatial aspect. This also meant that the scope of this project ended up being too large for a couple of weeks. What I will be presenting today is where the project is currently at and all the steps taken in order to be at this current point. On the right are what was proposed to be done for this project. It was intended to first figure out what datasets would be appropriate for this project, and then understand how the model is currently working. Then I would implement a single places dataset into the current model to make sure that everything is working before moving forward. I would also see how well it does at predicting this singular dataset. Next, I would have multiple places, data, all be included to add the spatiality to the model and see how well the model did at predicting. The first task to complete for this project was choosing an appropriate dataset to use. To start, we had to use data that would be specifically for long sequence time series forecasting. Another important point of consideration was using a reputable dataset. The dataset needed to be known and commonly used by the community in order to be compared to other models' results and give some validity to the results found at the end. Lastly, we wanted datasets to be main specific if possible and choose to stick to renewable energy. This was more of a personal preference as it related to where we live and could be beneficial to our community. Because of these reasons, a solar power and wind dataset were chosen. The solar power dataset has 1 year of 5-minute solar power and hour day ahead forecasts for approximately 6,000 simulated PV plants from the year 2006. From this, the main specific data was used, which accounted to 23 different locations with approximately 105,000 data points taken at each. The wind dataset has approximately 13,500 different places checked, with about 8,300 data points taken at each from the year 2021. Another important step was understanding fully how the model was being used. This may seem as an obvious step, but when adding additional code to a currently existing model, every part of the current code needs to be understood in full in order to prevent the model from breaking and do specifically what is intended. This part took quite a bit of time throughout the project as new problems were discovered which required an extensive knowledge of the model to solve. It was also important to understand why they chose to do different parts of the model in order to create my own additions that would work with the current framework. The Informer model was intended to be adaptive to outside users' applications. Because of this, they have options to use their model with preset datasets or with your own dataset. Here, the model was set up in Colab with the custom dataset structure, using a sample from each of the datasets. This was done first in order to make sure the model was being used correctly and there were no issues with the dataset being used. Some issues did occur with the structure of the datasets not being compatible with the model, but some rearranging and removing of NaN values solved these issues. On the left is some results from this simple test of the custom dataset. While this isn't a great prediction, very little training was done, and this test shows that the custom dataset was in fact working with the model. On the right is an example of all the pre-set up data loaders, where the custom is what was used for this project. There is also the code used to remove the nan values from the dataset. Moving forward with the project, it was determined that a new embedding should be made in order to allow the model to learn from the different locations. It was chosen to make this a trainable embedding so that the model would be able to learn from different locations to be able to predict their features better based off of previous data from their location and previous data from nearby locations. In order to do this, time was spent learning from the other embeddings in the model, as well as how simple embeddings are created. The resulting embedding was added into the code, and the current code was adjusted in order to accommodate adding it in. This was then tested separate of the full code to make sure it worked, then in a custom dataset collab. The data files also had to be adjusted in order to accommodate for the new location embedding by moving around what was currently there and adding in latitude and longitude columns. Shown is the part of the result of a simple test using a model summary to check if the embedding compiled correctly. After creating the new embedding, it was discovered that a custom data loader would be needed to be created as well. This is needed to accommodate using multiple locations datasets. Currently, the model iterates through the whole data CSV file training on batches from it. This becomes a problem when the CSV file contains more places than just one. When training, we do not want it to look at a batch of mixed location data at the cusp of where one location's data ends and another data begins. The image shown is used to better depict what the issue being presented is. Because of this, a new data loader needed to be created and used. In order to create a new data loader, time was spent learning the structure of data loaders, how simple data loaders are created, and how the data loaders currently in the model work. This is where the project is currently at. Here is the revised timeline of the project. While the first couple milestones were achieved, as the project progressed, new steps had to be taken to enable it to work, which made the scope of this project too large for the time frame provided. Added in was learning how to make an embedding and creating an embedding to account for locations on the data. Then the datasets were adjusted in order to work with the new direction of the project. Lastly, was learning how to make a data loader and creating a custom one to prevent training of false or incorrect values. Here are the references I used in order to make this project. Thank you for watching.